Hey everyone, we are about to go up to our eyeballs in definitions and a little bit of logic. So let's dive right in. We're looking at differentiability and continuity. So a few definitions, and we're going to have to go off on a little bit of a tangent when we deal with these definitions. So looking at differentiability at a point. So function f, and these are just the definitions you see in the book. And it's really good practice to get used to reading these definitions and figuring out what they really mean. Because you can read something, and even though you know all the individual words, when they're put together in the order that you read, you might not get it. And that's okay. We're learning how to read these books and read definitions and such. Okay, so function f is differentiable at x equals c if and only if f prime of c exists. Okay, I'm going to hit the brakes right here, right now, because of this phrase right here. If and only if. We need to talk about the phrase if and only if. So in logic, you get these if-then statements. For example, if it's a frog, then it can hop, which is true enough. But for an if and only if, that would mean it's a phrase that you could switch the direction around. For example, if it can hop, then it's a frog. I don't know if you could read that because it's a little dark. And that's not true. It could be a bunny. So looking at some slightly silly examples, but hopefully it will help us understand the phrase if and only if. So say we have this shape right here. If a shape looks like a combination of a triangle and a bottom, then that shape is a heart. I would call that a true statement. If I switch the order around, like instead of going if P then Q, I switch it to if Q then P, I just swap it. If a shape is a heart, then it looks like a combination of a triangle and a bottom. Both of these statements are true. If you just kind of go with my slightly wacky example here. Since both of these statements are true, you can say if P then Q, and also if Q then P, you can just switch it around. This means we can use the phrase if and only if. A shape is a heart if and only if it looks like a combination of a triangle and a bottom. So the if and only if means we can switch things around in either order. So you can read it basically forwards and backwards, and it's going to be true no matter what. We have a lot of things that are not true, like if it's a frog, then it can hop. But we can't switch that order around. There's a lot of examples like that. It's actually really hard to come up with an example that the if and only if thing works. You see if and only if a lot in computer programming. Let's get rid of these things. Okay, so going back to here again. So differentiable if and only if f prime of c exists. Or it's differentiable at c. So it's differentiable at c if and only if the slope exists. Well, okay, that sounds fair. Some of these definitions are kind of duh. And that's okay too. Okay, second one, differentiability on an interval. So instead of on a point, we're on an interval. Well, this isn't exactly rocket science. It's differentiable on an interval if and only if it's differentiable for every x value in the interval. Well, okay, that makes sense. Differentiability for the interval if you have slopes everywhere. Sure. And then differentiability definition is function f is differentiable if and only if it is differentiable at every value of x in its domain. So that's saying just for the entire function, not just an interval, not just a point. So we're going from small to big here. But it's just talking about differentiability. This leads us to a property. And that property is the fact that differentiability implies continuity. If a function f is differentiable at c, then f is continuous at c. That makes good sense because for differentiability to happen, it's a limit and it has to happen from both sides, so you have continuity. That seems pretty reasonable. Now, in logic, they spend a lot of time with logic, switching orders around, and let's play with this a little bit. So one way people will take an if-then statement, like if P then Q, they'll switch it around and just switch the order, and that's called a converse. It's not just shoes. So the converse would be if you just switch the order around, if continuous, then differentiable. That's not, it can be true. And just because something can be true doesn't make it true, because it's not true all the time. For example, if you have an absolute value graph, like it's continuous, but it's not differentiable at the corner. So as soon as you can come up with one single counter example, you've done it. That's kind of a cool thing. So another way people like to switch things around is doing what's called the inverse. The inverse is where you keep the order as the original order, but you make them both negative. If not differentiable, then not continuous. So here's your counterexample. Actually, same graph again. It's not differentiable at C, but wait, it is continuous. So that way doesn't work necessarily. And now here's a cool thing. If you have an if-then statement that's true, like if differentiable at x equals c, then continuous at x equals c, if you make both things negative and you switch the order, it's like you put converse and inverse together. It's called a contrapositive. And a contrapositive is always true. If not continuous, then not differentiable. Well, that totally makes sense, right? You can't draw a counterexample of that. Like, try to find a spot that you have not continuous, where you do have a slope. You can't have a slope where nothing's there. So the contrapositive is always true. We are not doing a whole lot with this section of the book. We don't really need to. You're going to basically just be looking at a few graphs and deciding if things are differentiable or continuous or neither or both, and drawing some examples showing all of those things.